All right, so now we're going to start talking about conservation of momentum. Um, like energy, momentum is a quantity that is conserved, which means the total momentum in the universe will always remain constant. It'll always be the same. In this lesson, we're going to learn how to apply conservation of momentum to everyday situations. So, when you think about if the total momentum in the universe is always the same, that means that we have zero total force. Okay. Momentum of an object can't change unless an external force acts on the object. So, in order for there to be conservation of momentum, there has to be a total force or a net force of zero. And that's true of the entire universe. But our entire universe is a really big thing to look at. So a lot of times we'll talk about systems, okay? So we'll talk about systems, and that's just an imaginary grouping of things. With my freshmen, we kind of talk about this as school systems, right? We have a Alta Aurelia High School and Alta Aurelia Elementary, and then we have Alta, or we have Aurelia Elementary and Aurelia Middle School. And over here we have Cherokee Public Schools, and in Storm Lake, um, we have the Storm Lake Early Learning Center and Storm Lake Middle School and Storm Lake Elementary School, and we have Storm Lake High School, and we have Storm Lake St. Mary's. Okay, oftentimes when we're talking about systems, we're talking like school systems, we're talking about community school districts, right? So we would draw a system, which oftentimes we draw as dotted lines when we're drawing a system out. So we would say that's the Alta Aurelia Community School District system. And then we have the Cherokee Community School District system. And we have the Storm Lake Public School system. And we have the Storm Lake Private School system. But we could also say, maybe we're talking about the Northern Iowa or Northwest Iowa school system. So maybe we still have these subsystems, but we could draw a dotted line around this larger system. Okay, so a system is just a group of objects that we put together, and there's this imaginary boundary around them. And when we have this imaginary boundary, we have internal forces and we have external forces. So internal forces are acting between objects that are inside the system. That would be like the buses traveling between the schools in the Alta Community School District. They're staying inside that system. But there are also external forces where you have interaction between these systems. So things can come into the system or leave the system. That's an external force. So that's something happening between your system and outside of the system. So we need to understand the difference between internal forces and external forces. Um, so the reason that we need to understand this is because only external forces can change a system's momentum. Internal forces don't have any change on the system's momentum because Newton's law states that every action has an equal and opposite reaction. So as long as those equal and opposite reactions are happening inside of the system, we still have the same amount of momentum. As soon as those things start happening outside the system or between two systems, that's when we have a change in momentum. The total amount of momentum in the universe is always the same, but we only have conservation of momentum in systems if we have only internal forces working in that system together. So, in a system with no external forces, we're going to have that so first of all the book wants us to take note that the total amount of force in a system is equal to the sum of forces internally There's no sum here. So the total force on the system is the sum of all of the internal forces plus the sum of all of the external forces. Okay, so that's our total amount in the system. And as long as our internal system is operating under Newton's third law, we're always going to have a paired reaction. So this inside of our system should be 0 every single time. The internal force is going to be 0 because you're going to have forces acting on objects, but there's going to be an equal and opposite reaction. So the total force is just going to be equal to the sum of your external forces. Um, this is a really big simplification. It just means that we never have to consider internal forces when we're calculating the total force on a system. Once you get farther into physics, if you do choose to go further in physics, you're going to realize that this is a lie. But it's a simplification in order for us to learn about forces and conservation of momentum. So momentums can vary as the total is conserved. As long as there's not an external force acting on the system. So if there's no external force acting on the system, that means that our total force is 0, or the sum of all of our forces is 0. And that means that our momentum before is equal to our momentum after. This is conservation of momentum. So as things are happening within our system, because it's in a system and we don't have any forces coming in, our total momentum stays the same. The individual momentums might change, but the sum of all of our momentums stays constant. The total momentum in the system at the beginning is the total momentum in the system after. It's really similar to conservation of energy, right? The types of energy may change. The energy of objects, whether it's kinetic or potential, is going to change, but the sum or the total energy always stays the same. So if we had 3 objects, right, for example, the initial of those 3 objects is going to equal the final of those 3 objects. But maybe my P1 initial is 2 kilogram meters per second plus 5 kilogram meters per second plus 3 kilogram meters per second. And maybe after all of the collisions, I have 1 kilogram meter per second plus 3 kilogram meters per second plus 6 kilogram meters per second. So these don't stay the same, but the sum stays the same. 2 plus 5 plus 3 is 10. 1 plus 3 plus 6 is 10. My momentum before, 10, is the same as my momentum after, 10. But the momentum of those individual objects has changed. So in order to do conservation of momentum, we always have to find the total momentum before, the total momentum afterwards. And sometimes we'll have missing pieces that we use conservation of momentum to find. So I'm going to give us an example. And I don't like the example in the book, so I'm going to give us an example from your homework. So this is the packet that you have. And I'm going to go ahead and do an example of number 1. So we have train car of 10 tons moving 4 meters per second towards a train car that's 30 tons that's just sitting there. It's 0 meters per second. And then after, so this is before, after these two train cars are hooked together, and it's asking us what is their resultant velocity. So in order to do this, we have to understand conservation of momentum. Our momentum before equals our momentum after. Our momentum before is going to be the mass of car 1 times the velocity of car 1 plus the mass of car 2 times the velocity of car 2 equals after, and this gets a little bit tricky because in order to do some of these problems, we're going to talk about collisions a little bit. But when they stick together, it's only really one object now, right? So I'm going to have mass of my third object times its velocity. Well, I know the mass of my first car is 10 tons times its velocity is 4 meters per second, plus the second car is 30 tons, its velocity is 0, equals the mass of these two cars after they collide, if they're stuck together, is just going to be the two car weights added together, right? 10 tons plus 30 tons is 40 tons. So my mass here is going to be 40 tons times some unknown velocity. If I wanted to, I could also say this is 10 tons times it's moving at a velocity plus 30 tons moving at an unknown velocity. Okay. Both of these are right. Both of these get us to the same place mathematically. So 10 times 4 is going to be 40 plus 30 times 0 is 0 equals 40 times V3. If we divide both sides by 40, we get 1 meter per second is my V3 or my final velocity. Hopefully that makes sense. We're going to do problem 3 as an example as well. So again, conservation of momentum, my P before, or my momentum before is equal to my momentum after. So for these problems, I think it's really helpful to draw things out. But the problem says a football player runs at 8 meters per second. So this is my football player running. And he plows into an 80-kilogram ref that was standing on the sidelines. So that's before. And after, the perfectly elastic collision, what that means is that the football player then stops and he's transferred all of his momentum to the ref who goes flying in the air. Okay, that's what perfectly elastic means for today. So I'm going to take my information. He's running at 8 meters per second. We don't know his mass, right? That's what it's asking us to find. The velocity initial of the ref is 0 meters per second because he's just standing there. And his mass is 80 kilograms. And then our final velocity of the football player is going to be 0 meters per second. The ref goes flying at 5 meters per second. The ref's mass still stays the same. And we still don't know the mass of the football player. But we can use conservation of momentum to figure this out. So my P before equals my P after, which means it's my momentum of the football player plus the momentum of the ref equals the momentum of my football player plus the momentum of my ref afterwards. The momentum of my football player is going to be 8 meters per second times his mass. We don't know what his mass is yet, so we're just going to leave it as an M. Plus the momentum of my ref, velocity times mass. His velocity is 0. He's got 0 momentum. Equals the velocity of my football player after the collision. He's just standing on the sideline now. So his momentum is 0, plus the momentum of my ref. 5 meters per second times 80 kilograms is going to give me 400 kilogram meters per second. So now I have 8 meters per second times the football player's mass equals 400 kilogram meters per second. Hopefully you can do the math on this and figure out that our mass of the football player is 50 kilograms. Okay, so those are some examples of conservation of momentum. You should now have the tools to do this conservation of momentum worksheet. Remember that momentum before equals momentum after.